I am now going to give you a brief introduction to radiation and production of radiotracers using cyclotron facilities. Nuclear medicine uses radioactive pharmaceuticals, also called radiopharmaceuticals or radiotracers, to diagnose, evaluate, and treat diseases. It includes two main diagnostic imaging modalities, PET and SPECT, and a treatment modality, molecular radiotherapy. Now, the focus of this workshop will be on the two diagnostic imaging modalities, PET and SPECT. So let's see what happens in these two modalities. Well, first of all, we need to obtain or produce a radionuclide, which will be the source of radiation. Then we need to incorporate this radionuclide into the drug or pharmaceutical we want to study. And once we've done that, we administer the radioactive pharmaceutical to the patient, and we wait for it to accumulate at the tumor or other target sites and clear from the rest of the body. Then we scan the patient and detect the radiation emitted by the radiopharmaceutical accumulated at the target sites. And finally, we view and analyze the images that will show how the radiopharmaceutical is distributed in the body and where those target sites are located. So as you can see, nuclear medicine involves the use of radiation. And what's radiation? Well, radiation is energy that comes from a source and travels through space and may be able to penetrate various materials. So for example, light, radio, and microwaves are types of radiation, but these are called non-ionizing radiation. Now, the kind of radiation discussed during this session is called ionizing radiation because it can produce ions, charged particles, in matter. So ionizing radiation is produced by unstable atoms. Now, these atoms are different from stable atoms because unstable atoms have excess energy or mass or both. Atoms with unstable nuclei are said to be radioactive. And in order to reach stability, these atoms give off or emit the excess energy or mass. And by doing so, they turn into another element. Now, these emissions are called radiation. And sometimes isotopes decay from one stable isotope into another unstable isotope continuously in a long radioactive chain until finally stability is reached. The kinds of radiation, well, the kinds of ionizing radiation are particulate, where mass is given off, and electromagnetic, which is like light. So gamma radiation and X-rays are examples of electromagnetic radiation. Gamma radiation originates in the nucleus of the atom, while X-rays come from the electrons. And alpha and beta radiation are examples of particulate radiation, both originating in the nucleus of the atom. Alpha particles, due to their charge and mass, they interact very strongly with matter and only travel a few centimeters in air. So they cannot penetrate the outer layer of dead skin cells, but if you ingest an alpha-emitting substance, it can cause serious damage. Alpha-emitting radiopharmaceuticals, for this reason, are used for radionuclide therapy. So what about beta radiation? Well, beta radiation has smaller mass than alpha particles, so beta radiation can travel a few meters in air and can be stopped by a thick piece of plastic. Beta radiation can penetrate the skin a few centimeters, and therefore it can pose a certain degree of external health risk. However, the main threat is still primarily from internal emission of ingested material. And finally, gamma radiation, unlike alpha and beta, it does not consist of any particles. Instead, it consists of a photon of energy, so it's like a light. And as they have no mass or charge, gamma rays can travel much further in air than alpha and beta particles. And gamma radiation can be stopped by a thick or dense enough material such as lead. So during this workshop, we will be focusing on positrons and gamma rays. So how is radioactivity measured? Well, the international system unit is the becquerel, which represents a rate of disintegration of 1 disintegration per second. So for many years, and still in some countries, radioactivity was expressed in curies, which corresponds to the radiation emitted by 1 gram of radium, which is the radioactive element found by Marie Curie. But due to the high value of 1 curie, microcuries and millicuries were very commonly used. And since then, physicists adopted a more logical unit, which is the becquerel, which, as I said, corresponds to 1 disintegration per second. So the associated inconvenience here is that the becquerel is a very small unit, so megabecquerels and gigabecquerels are commonly used. So here you can see the conversion factor from curies to becquerels. So how can you protect from radiation? Well, the guiding principle of radiation safety is ALARA, which stands for as low as reasonably achievable. This principle means that even if it is a small radiation dose, if receiving it has no direct benefit, then you should try to avoid it. Now, to do this, you can use 3 basic protective measures in radiation safety: time, distance, and shielding. So time simply refers to the amount of time you spend near a radioactive source. And you should minimize your time near the radioactive source to only what it takes to get the job done. So finish as soon as possible and then leave the area, because half the time spent means half the radiation dose received. Distance refers to how close you are to the radioactive source. So you should maximize your distance from the source as much as you can, because distance and dose are inversely related. So if you increase your distance, then you decrease your radiation dose. And finally, to shield yourself from a radiation source, you need to put something between you and that radiation source. So as we have seen before, the most effective shielding will depend on what kind of radiation the source emits. And some radionuclides emit more than 1 kind of radiation. So this obviously has to be taken into consideration when choosing the shielding. So what happens with PET radionuclides? Well, we said PET radionuclides emit positrons, which can travel a relatively short distance. Now, during this travel, they can meet an electron. And when a positron and an electron collide, they mutually annihilate, and they produce 2 gamma rays that are emitted in opposite directions. And it is these gamma rays, and not the positrons, that a PET scanner will detect. So these gamma rays have high energy, and they require thick lead for effective shielding. Radionuclides used for SPECT also emit gamma rays, but these are generally lower energy gamma rays than the ones emitted by PET isotopes. And therefore, they do not require that much lead for effective shielding. So for example, while in order to reduce the intensity of radiation of a PET isotope by half, the thickness of the lead needs to be approximately 6 millimeters. For technetium, that thickness is only 0.33 millimeters. So as a consequence of this, in all radiochemistry laboratories, PET centers, or any areas where PET isotopes are used, there is a lot of lead around. And this obviously has cost implications when designing a PET radiochemistry or scanning facility. Similarly, areas where there is radiation will display many signs and warnings about the presence of radiation, and in some cases also indicating the type of radiation, which radioisotope, and how much. These areas are controlled, and entry is restricted to radiation workers. So if you are a radiation worker, you will have personal protective equipment you can use to minimize exposure. You may also have alarming dosimeters to help manage the time and track your accumulated doses in areas with elevated radiation levels. And if you are handling radioactive substances, your hands may receive a high radiation dose, and this needs to be closely monitored. And this can be done using these rings shown in this picture. So if you're a radiation worker or a patient receiving radiation, it is important to monitor the radiation you receive. But how much radiation is too much? just measuring the amount of radiation you are exposed to isn't that helpful. So instead, we need to know how much harm that radiation can do if it gets into your body, especially if it's ionizing radiation. So yeah, just knowing there is radiation around you isn't that helpful in working out how risky it is. So instead, you need to understand how the different sources and types of radiation cause biological damage. And this is measured using sieverts, which are a measure of the potential biological impact of exposure to ionizing radiation, and in particular, how this exposure might lead to problems by damaging your DNA. So this helps us understand, for example, how much exposure to radiation might increase the chances of developing cancer. So to do this, sieverts combine three aspects of radiation: the amount of energy that radiation is capable of dumping into your body, and this changes with different sources and situations, the type of radiation, and then which part of the body is being exposed. So by combining these three factors, you get a good idea of how much damage the exposure might cause. And with this in mind, those limits are set to protect workers and members of the public from the effects of ionizing radiation. So they are set at a level that balances the risk of exposure with the benefits of using ionizing radiation. And the fundamental requirement is for employers to reduce all exposure to ionizing radiation to as low as a level as possible, as this should be, and this should always be below the dose limits. Now, those limits are intended to reduce the risk of serious effects occurring, such as cancer, and they are in place to protect the eyes, the skin, and also the extremities against other forms of damage. And depending on the dose staff are likely to receive, they may be classified. And if they are classified, then, for example, they will need to have mandatory medical surveillance regularly. But it's also important to put things into perspective. And we are all exposed to natural radiation sources, which come from the Earth, such as rocks and soil, and the outer space, cosmic rays, and the food we eat. A smaller amount of radioactive material exists naturally in our bodies. And every year, each person is exposed to natural radiation and also a variety of other sources, such as color TV sets, air travel, which increases the exposure to cosmic radiation due to higher altitudes. So here in this list, you can see estimated radiation doses for different activities, such as watching TV, traveling by plane, having a mammogram, just the dose you get by living in the UK every year, what an FDG PET study may give you, and what the tumor receives during a cancer treatment. So due to the use of radiation in nuclear medicine, there are certain regulations that apply. The control of radiation exposure to individuals while at work, including persons exposed as a result of the employer's work activity, is covered by the ionizing radiation regulations. And the main aim of these regulations is to establish a framework for ensuring exposure to ionizing radiation arising from work activities is kept as low as possible without exceeding those limits that I showed you earlier. So health and safety inspectors have statutory powers to assist them in enforcing these regulations. And the Environment Agency ensures that all radioactive waste is managed safely with no acceptable risks to people or the environment. In these pictures here, we can see how different things were before the introduction of regulations, when they still didn't know so much about radiation and no shielding was used here. There was no PPE, so you can see no gloves, direct contact with radiation sources. And in this picture, for example, you can see that operators are wearing full PPE, protective measures and shielding is being used, credentials, and so on. So now let's go back to talk about how radiopharmaceuticals are made. I mentioned earlier that in order to make a radiopharmaceutical, we first need to obtain or produce the radioactive source, the radionuclide. So how are radionuclides generated? Well, for most radiopharmaceuticals used in PET, this radioactive source is generated in a cyclotron, which is a compact particle accelerator. Cyclotrons nowadays look like these images here. In some cases, like the cyclotron at the bottom, they need to be placed into a concrete bunker, which is usually about 1 meter thick, with interlocks on the entrance door. But in some other cases, like the cyclotron on this image, they can be self-shielded if they are constructed with a concrete lead mix. Well, as you can see on this picture here on the right, cyclotrons are not new. The cyclotron was invented in 1931, and Lawrence was awarded the 1939 Nobel Prize in Physics for it. So what does a cyclotron actually do, and how does it create the radionuclides? Well, a cyclotron is not a simple piece of equipment, and it will be seen differently by different people. So here we will try to explain this in a simple way. So we will focus on this middle picture. So the cyclotron body consists of 2 electrodes called Ds because of their shape, this one and this one. So these Ds are in a vacuum chamber, which sits between the poles of a large magnet that creates a magnetic field. So a stream of charged particles is fed into the center of the chamber, and a high-frequency alternating voltage is applied across the electrodes. So this alternating voltage attracts and repels the charged particles, causing them to accelerate. And the magnetic field moves the charged particles in a circular path. So as they gain more energy during the acceleration, they spiral outwards until they reach the outer edge of the chamber. So here, at this outer edge, what we do is we put a non-radioactive isotope. And when this non-radioactive isotope reacts with this stream of charged particles that come from the cyclotron, a nuclear reaction occurs and a radioactive isotope is produced. So this will be the radiation source. So by changing the non-radioactive isotope that you put at the outer edge of the chamber, different nuclear reactions will take place, and therefore different radioisotopes can be produced. So in this example here, for example, they have placed nitrogen at the outer edge of the chamber. So when the protons are accelerated in the cyclotron and they hit this nitrogen, carbon-11, the radionuclide, is produced. Here I have listed the radionuclides that are most commonly used in PET, along with their half-life and some examples of radiopharmaceuticals produced from these radionuclides. So as you can see, most of these radionuclides have very short half-lives. And by the way, half-life is the time it takes for radioactivity to halve. So if we look at this example graph here, F18, for F18, for example, it takes 2 hours for the radioactivity to decay from 1,000 megabecs to 500 megabecs. But for copper-64, it takes 12 hours to do the same. So the shorter the half-life, the faster you need to work to produce and inject a radiopharmaceutical. And it is for this reason that radiopharmaceutical synthesis must be as simple as possible, automated with the use of robotics, and as quick as possible. So here you can see some examples of synthesis modules. Some of these modules use disposable cassettes that are specific for the radiotracer you want to synthesize. So you can buy the cassettes you need along with the reagents or ingredients for the synthesis and connect everything to the synthesis module for the synthesis to happen in an automated way. But as there is a lot of radiation involved during the synthesis process, shielding must be in place to protect the operators. And therefore, those synthesis modules I just showed you in the previous slide must be placed inside hot cells, which are radiation containment chambers like the one you see in this picture. So while the radionuclide is being produced in the cyclotron, the operator prepares the synthesis module, adds the required reagents, and checks everything is ready for the synthesis to happen. So then the operator closes the door of the hot cell, and the radioactivity is delivered from the cyclotron to the synthesis module inside this hot cell. The operator can then follow and control the synthesis through the laptop. And then at the end of the synthesis, the radiopharmaceutical is delivered to a vial that sits in a lead pot. The operator will then dispense the radiopharmaceutical and perform QC checks before it is released for patient use. Radiopharmaceuticals are medicinal products and therefore must be made in line with the UK Human Medicines regulations. The manufacturer must follow the GMP principles, and GMP is an integral part of quality assurance, which ensures that products are consistently produced and controlled to the quality standards appropriate for their use. The basic requirement of GMP is that all manufacturing processes are clearly defined, reviewed, and shown to be consistent, to consistently produce the pharmaceutical of the required quality standards and specifications, and that all critical steps or any significant changes to the procedure are validated. It's for this reason that GMP covers all aspects of manufacturing, from starting materials, equipment, premises, documentation, training, personal hygiene, etc. So how long does the production of a radiotracer take? Well, let's use the synthesis of FDG as an example. So first we need to produce F18 in a cyclotron. This takes about 2 hours. And during this time, the operators will prepare the synthesis module and the reagents. At the end of these 2 hours, let's imagine we have made 70 gigs of F18. We then need to deliver this radioactivity from the cyclotron to the synthesis module in the hot cell, which can take about 15 minutes, and then do the synthesis, which let's say takes 30 minutes. So just because we've spent 45 minutes in this process, our original 70 gigabecquerels have decayed to just 52 gigs. We then dispense the radiotracer and perform QC checks. This can take another 45 minutes. So at the end of this, we could have 39 gigabecquerels. But this is assuming that we have had no losses and that the yield of the synthesis is 100%. Well, in reality, this is lower. And for FDG in particular, this is approximately 70%. So at this point, we can expect to have about 25 gigabecquerels in reality. If the QC checks are satisfactory, then the radiotracer is released for use and can be shipped to the hospital. The scanner can be on site or can be at some distance. So if we need to use a courier to ship the tracer, then we will need to use an appropriate courier and a type A container, like the one shown in this picture here, which protects the contents and provides sufficient shielding during transportation. If the hospital is, let's say, 45 minutes away, then from the original 70 gigabecquerels we started with, we can expect to get about 19 gigabecquerels when it gets to the scanning site. So now I'm going to show you a quick video of what happens once the tracer is injected into the patient. So that was the end of my presentation. So thank you very much for listening. And I will be happy to answer any questions you may have during the Q&A session later on.